Hello. Today we are talking about the normal curve and looking at some things that are normally distributed. So a normal curve is a bell-shaped curve, and you see an image of that bell-shaped curve on your screen. In the normal curve, we have the mean in the middle. So this tick mark right here in the middle is the mean, and typically a Greek letter mu is used to represent the mean. Moving away from the mean, we learn from the empirical rule that almost all of the data is within 3 standard deviations. So the remaining tick marks, if I am moving to the right, are the positive, and they are plus. So from the mean, you add. This is 1 standard deviation, and we use the Greek letter lowercase sigma, which looks like our O with a little tail, but it's not a 0, it's a sigma. And then we would add 2 standard deviations, and finally 3 standard deviations, and that would get almost all of the data that is larger than the mean. There is perfect symmetry within the normal curve, so we do the exact same thing going to the left, but for the left we're subtracting. So this is 1 standard deviation below the mean, or -1 standard deviation, -2 standard deviations, and -3, or subtract 3 standard deviations. Now, we are told up here at the beginning, so in the green part of the screen, that the average amount of DNA a person shares with a sibling is normally distributed with a mean of 50%. So going to the middle, the mean represents 50% of my DNA matching my sibling. It then tells me that it has a standard deviation of 4%. So the standard deviation tells us how far things are spread from the mean. So what we're going to do is, on the right side of the curve, we're going to add, and on the left side of the curve, we're going to subtract. And in the middle of our curve is the mean. So we're going to start with the positives. I always start with the positives. And so 50 plus 4 means that in order to get to the first standard deviation, that would be sharing 54% of my DNA with my sibling. And then I add 4 again to get to the 2 standard deviations, so plus 4 again, so 54 plus 4 would get me to 58% of my DNA is a match to my sibling. And then I'd add again, so 58 plus 4 would say 62% of my DNA is a match to my sibling. Then we'll go to the opposite side, so from the left of the mean, the negative values, we're going to subtract on this side. We're starting with 50 in the middle and moving down, so 50 minus 4 gives me 46% at a standard deviation below. Subtract 4 again. So 2 standard deviations below would be 42%, and subtract 4 again, and so 3 standard deviations below would be 38%. Now, we had talked about the empirical rule in our notes and in our pre-lecture, and so we know that like 99.some% of the data is from -3 to +3. So every pair of siblings out there, or I really should say almost every pair of siblings out there, would share somewhere between 38% and 62% of their DNA. So on average, it's 50%, but we know that nobody's exactly average, or very few people, so most people are going to be a little bit more, a little bit less than 50%. And then really almost everybody would be between 38 and 62%. So then we have a question at the bottom of our screen, and it asks us to identify where 56% would be on the curve. So 56%, I'm looking at the percentages I labeled. So here's 54, here's 58, and I can see 56 would be smack dab between the two. So I'm going to put a line dividing my curve into 2 sections. So this line represents sharing 56% of my DNA with a sibling. And so to the left, this big section would be where we share less than 56%. then the small area to the right is where I have labeled 58%, 62%. So the small area is where a person and their siblings share more than 56%. And then it tells us here to shade the area of the curve that represents the probability of sharing 56% or less. So doing some shading here in this big section because that would represent 56% or less. So 56% is the line exactly, and then this shaded area is less than. So our next question is to estimate the probability as a percentage that your DNA match to your sibling is 56% or less. Choose the answer that is closest to the correct percentage. So I'm going back to my picture, and my question is about this big shaded area, and I'm supposed to estimate what percent of the area under the normal curve do I think I have. So there's some things that can help me. First off, I know that the normal curve is symmetrical, so the two halves are equal, and I know that the middle is here at the mean. So to the left of the middle is 50%, and I have that full area. So I have at least 50% of the normal curve here. To the right, I also have a big section because we can see that the normal curve from the mean really dips down to get that bell-shaped curve. And so as I move past my line at 56%, there's only a small section beyond that. So looking at the multiple choice options, letters A, B, and C are distinctively wrong because we notice that the mean and half of the curve is in our shaded area. So we have more than 50%. So that leaves my options as letter D or letter E. We also noticed that up to the 56% line was a big section because it was part of the tall section of the bell curve. So my best estimate is going to be that 90% of sibling pairs out there would share 56% or less of their DNA. So let's just go back and look at that curve one more time. And so we're suggesting that the shaded in area represents about 90% of all of the space underneath that curve. And so our next question is then what percent would be above? So what is the percent of sibling pairs that share more than 56%? And so we bring into play one of the key characteristics of the normal curve, and that is that 100% of the data is under that curve. So we estimated that 90% of sibling pairs share 56% or less of their DNA. And so we need the number that would add up to 100 with 90%. And so that would mean that 10% then share more than 56% of their DNA. And so we use a number of the properties that we learned about in pre-lecture. Specifically here, we're using that the percentages add to 100. And we're using that the mean is in the middle, so truly dividing the curve into halves, each half being 50%.